gosh, it's so good to see you. Just kidding. I don't know if I can do a video with this camera in my face. And I don't really think there's much of a point in seeing my face anyway, but we'll leave it for today, and it's dark anyway, and whatever, we'll see how it goes. So I decided to make a video because it seems to be what the kids like these days about series convergence. Okay, here's the deal. We've studied how to write a series, whether we construct it from Taylor series or whether we construct it from another series that we know, whether we construct it from it being a geometric series. And now we're about to take a turn and talk about how we know whether a series converges or not. So we talked about it a little bit because we talked about geometric series, but we haven't really gotten deep into the convo. So there are 5 series convergence tests, and we need to talk about all 5 of them. This video is going to address the first 4 because they're not too bad. Then there'll be a whole nother day. Is that how you say it? A whole nother day? I'm pretty sure nother is not a word. There will be another whole day, English, on the 5th test. So to go through here, the nth term test is the first one, geometric series, integral test. Oh, wait for the fun fact. So exciting. Direct comparison test. And then the 5th one is called the ratio test. And that will be a whole big lesson in and of itself. The ratio test is actually the most commonly used one. So why are we even doing the other ones? I hear ya. Just kidding. We'll use the other ones too. So we're going to go through these first 4 today. Obviously, I'm in a strange mood, so we'll see if I can just rope it in and do the lesson. So I think it's just because you guys aren't here in front of me, like I find the need to entertain myself. So, okay. All right, I'm going to be looking at my computer screen, not really at the camera. Here we go. Okay, so the first test we have is called the nth term test. This is a test that we actually already know. The nth term test just says, if I look at a series and I look at the limit of that series as we go to infinity, the limit has to be 0 to even consider convergence of the series itself. So the nth term test is really just a test that can tell us whether we should continue or not. We're going to use the nth term test just to determine whether the limit goes to 0 or not. And if the limit does not go to 0, we don't continue. We just say, I'm sorry, but we're done. So the nth term test technically says, let's write up a technical definition. The nth term test says, I should have left myself more room, but whatever. If the limit of our series, I'm calling A sub n is our series. If the limit of our series as n approaches infinity, of course, does not equal 0, then the series diverges. Oh, so here's what I should say in the beginning. You're going to be answering the question, does the series diverge or converge? That's it. That's all we're answering today. We'll move on when we talk about ratio tests to if the series converges, then what is the interval of convergence? What is that? What are those x values for which the series converges? Right now, all we know is a geometric test has that certain window, and we know that like sine, cosine, and e to the x, their interval of convergence is infinite, negative infinity to infinity. So, but we're not there yet. All we want to know right now, oh, pardon me, very rude. Oof, a half yawn. You guys are boring me. Just kidding. I'm really sorry. It's just a day. What was I saying? Oh, so right now we're only trying to figure out, does our series converge or does it diverge? That's it. Answer that question. That's it. So we can start off with this. Every time I look at a series, I'm just going to test and see by the series or by the nth term test, is the limit equal to 0? Because if it's not, the series is going to diverge and I can stop doing the problem. That's really it. So I'm almost hoping that the limit is not 0 because so then I can just stop. Stop the madness. So here we go. Let's look at this example. Does this series converge or diverge? So every time I have one of these, I actually am going to stop and just think about the nth term test and think about whether that limit goes to 0 or not. So this is where we're thinking about growth rate. This is why we talked about growth rate before, what grows fastest, just so I can easily tell which is growing faster, the top or the bottom. So I'm just going to look at the limit as n approaches infinity of 2 to the n over n plus 1. Well, 2 to the n is growing a heck of a lot faster than n plus 1. So the top is growing way faster than the bottom, so this is going to infinity. Last time I checked, infinity does not equal 0. Therefore, the series diverges. Ain't no need to go any further. Once the nth term test tells us that that limit is not 0, the series is going to diverge. And this is true for something that even I didn't write this example up, but it would be true even if I had a series where I have n squared plus 1 over 2n squared. That's another good example. What is that limit? Well, if I look at the limit as n goes to infinity, look at the growth rate of the top and the bottom. They're the same. The top grows n squared, the bottom is n squared. So this limit would equal 1/2 ratio of the coefficients. Well, that ain't 0. So this series is going to diverge also. So that means my series diverges and I'm done. Now, important caveat. The definition of caveat is kind of like a warning. Important caveat. Just because you get a series whose limit goes to 0 doesn't mean it converges. It just means you got to keep testing. So all this test tells us is whether a series diverges or whether we should continue on and keep checking. So should I write that down? I feel like I should write that down. So I will also say, if the limit of a sub n as n goes to infinity does equal 0, it doesn't tell you nothing other than you should keep testing. Keep testing. Because it's possible that that series still diverges. We just aren't sure. We're going to have to find another way. Okay, test number 1. Test number 2 is also super easy. Geometric series test. We already know this. We know how the geometric series test works. We know that we are looking for A and R. A doesn't really matter for us. That's just the first term. R is what matters for us. So we need that multiplier. So a geometric series converges if the absolute value of R is less than 1. Remember, that means R has to be between 1 and -1. That's the geometric series test. There's not a whole lot to it that you don't already know, but I wanted to make sure we put it in this list of things so you can remember it. So if we want to do this example, does this series converge or diverge? Well, one way to know if a series is geometric or not is it typically has this form of something to the n. It won't have a factorial. It's going to be something to the power of n. If you're ever unsure, you can just grab some terms and see what happens. So let's just make sure that this is geometric. So let's plug in 1, we get 1/8. 2, we get 1 over 8 squared. 3, we get 1 over 8 to the third, and so on. Yep, that's geometric, and our multiplier is 1/8. So we just have to answer that question, is 1/8 between -1 and 1? Why, yes, it is. So therefore, because 1/8 is less than, or is between -1 and 1, this series converges. And that's really all you need for geometric series. So just wanted to make sure it was in the list. Okay, now the integral test. Bum, bum, bum. The integral test basically says, if I look at my series and I take the integral of that series, but I basically just replace the n's with x's because n's don't make a whole lot of sense in integral notation. I'll tell you about that in a second. But if I just look at the integral of that series, either both the integral and the series converge, or both the integral and the series diverge. So this is why we studied improper integrals before, so that we could just use this integral test. That's really the only reason that we did it. Sorry to put you through such torture. But the main crux here, I'll write it like this. There could be a lot of fancy words, fancy words, fancy words, fancy words. But basically, we're going to say, if the integral of our series converges, then the series itself also converges. And if the integral of our series diverges, then our series also diverges. So basically, if I can quantify the area under the curve, then I can also quantify the sum of the series. They're going to, if the integral grows slowly enough that I can quantify the area under it, then the series also grows slowly enough that I can add up all that. Makes sense. I mean, series and integrals are kind of doing the same thing. They're adding stuff up. So if an integral adds stuff up, a series adds stuff up. So they kind of do so at the same rate. But here's the real point of that. So, okay, if I have an integral that converges, the series will as well. The main thing I use here is that p-test. So do you remember the p-test for integrals? The p-test said if I have the integral of 1 over x to the p from 1 to infinity, as long as p was bigger than 1, the integral converged. Same thing's going to be the case here. But if p was 1 or smaller, the integral was going to diverge. So that same thing's going to apply. That's what's going to help us now. So let's recall this p-test. If I have the integral of 1 over x to the p, if p is greater than 1, the integral will converge. If p is less than or equal to 1, the integral will diverge. Remember we talked about like 1 over x? What happens with 1 over x? 1 over x obviously decreases, but it doesn't decrease fast enough for me to accumulate the area from 1 to infinity and get a numeric number. The area is still too big. But 1 over x squared grows slowly enough, or doesn't grow, decreases fast enough, so that if I go from 1 to infinity, I can quantify that area. This is the marker. This is the divider. Everything that has a power bigger than 1, I can quantify the area. The curve will be close enough to the x-axis to quantify the area. Everything with a power 1 or smaller will be too big. The space between the curve and the x-axis will be too big to quantify, to add up. So there's a lot of rules here. There's a lot going on, and it gets kind of confusing. If you can try to like stay in your lane and keep coming back to your notes, you will eventually maybe get it. So look at our examples. We're going to take some liberties here in how we think about these. But for example, does this converge or diverge? So first of all, let me explain that if I'm thinking about all of these tests, the first one I'm going to refer to is the nth term test. So if I'm going to look at this, I'm going to first think about the nth term test and just make sure the limit of this function will go to 0. Does it? Yes. The bottom's going to become infinity. The whole function is going to go to 0. So I know that I should keep testing. The second thing I would look at is this geometric? Well, no, it's not. You can plug in some numbers and see, but I don't have that something to the n idea, so it's not going to be geometric. Sorry. Sorry, I have a very important text to check. Isn't that hysterical? This is so boring for you. Okay, sorry. My little son had a question and I had to answer him. Okay, so does this converge or diverge? Well, nth term test tells me to keep testing. Geometric test tells me nothing. So now I'm going to try out the integral test. So I'm just going to see what happens. What would the integral of 1 over n root n be? Would that converge or would it diverge? And I'd be going from 1 to infinity, just like my limits of the series do. So what is this? I don't know. The power of this n is 1/2. The power of this n is 1. But I got to put it all together. I need to look at this as the integral of 1 over n to the something. Now, technically, I should change my n's to x's because with integrals, I'm really using x's, not n's. It doesn't really matter. We can just keep it like this. So this is going to be n to the power of, well, this is 1, this is 1/2. So n to the power of 3/2. Okay, now I can think about this. Does this integral converge or diverge? Well, this power, according to the p-test, is bigger than 1, so I'm all good. So this integral converges. Therefore, the series also converges. So that's all I'm talking about with integral tests. You just have to go see what's going on with the integral. It can get more complicated, but I'm pretty sure the AP test keeps it at this level where we really only have to think about the integral test in terms of the p-test. What's that power of p doing? As long as that power of p is bigger than 1, we're good. Integral converges, so does the series. If that power of p is less than or equal to 1, not good. The integral will diverge, and so will the series. So look at this second one. Does this series converge or diverge? So again, nth term test I'm going to try. Well, this limit will go to 0, so I should keep going. This is not geometric, so that won't help me. So then I want to look and see the integral test. That's the next test I want to use. So I want to look at the integral of 6n squared over n to the third plus 1. So I want to just see how are the top and bottom behaving and how can I reduce this? So we take some liberties here that seem a little bit like illegal, but you're going to be okay. So first of all, when I have this plus 1 on the bottom, it means nothing. It changes the value of that bottom, not at all. So anytime I have a plus, blah, 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 anything else, I always get rid of everything other than the lead term. The lead term is the only one that's important. So once I get rid of anything else that might be added or subtracted, I can compare these. Okay, well, I can really look at this as taking the 6 out, and the n squared over n to the third reduces to 1 over n. So what I'm really looking at is that integral. Does the integral of 1 over n converge or diverge? You should know the answer to that! Excuse me. It diverges. Go to the p-test. The p-test says if I have the integral of 1 over x to the p, this is the same thing as that. It's just not x, it's n, but it's the same thing. What's the p? The p is 1. Can p be 1? Not if you want it to converge. So therefore, this integral diverges. And therefore, the series also diverges. On the AP test, on the free response, you're going to have to give the test that you use. You're going to have to say, we know this diverges by the integral test. And that would be enough for them to know what you're talking about. Are you ready for the fun fact? Okay, so the fun fact, and we've already talked about this a little bit, but this series, 1 over n, oh my gosh, the lights just went out. Let me move around. There we go. This series, 1 over n, is called something special. I think I told you about it when we did the integrals, but it's called the, let's make it pretty, called the Harmonic Series. Really popular, famous name for it, called the Harmonic Series. And it diverges. It's the most famous divergent series in math. Wow, you heard it here first. It diverges, obviously, because of the integral test, because the power of n is just 1. Oh, n equals whatever, 1 to infinity. But not only does it diverge, here's the fun fact. I have it written down. It grows so slowly. So think about this is a sum. I'm plugging in n equals 1, 2, 3, 4, whatever. So I have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. And even though these fractions are getting smaller and smaller as I add on each subsequent number, when I add up this whole series, I get infinity. That's the whole deal. That when I add up all these numbers, I'm going to get infinity. This is too big to quantify. That's why we say it diverges. Well, even though it diverges, it eventually will become infinity. Guess how long it takes to give me a sum of 20? So think about it. The first term gives me a sum of 1. First 2 terms, 1.5. First 3 terms, 1.5 plus 1/3. First 4 terms, all of that plus 1/4. So I'm growing really slowly, right? So the question is, how long to produce a sum of, 20? Do you want to know? Do you want to know? Do you want to know? Who wants to know? Do you want to know? I'm not going to tell you. Just kidding. It takes 178,482,301 terms of, the series to produce a sum larger than 20. I mean, is that crazy? It takes 100, it just makes you think about how big infinity really is. It takes 178 million terms, almost 178.5 million terms, to produce a series, to produce a sum larger than 20. But yet the sum is still infinite. So how long must it take to get a sum of 100? A jillion? How long till to get a sum of 1,000? Like a Googleplex, a Googlebillion? It's crazy. It grows so slowly that it still takes 178 million terms to get to a sum of 20. But yet we're going to get to a sum of infinity in the end. That's crazy. Okay, you hanging in there? You okay? We got one more test left for this video. Test 4, DCT. Direct comparison test. You know how mad I would be if I stopped this and the audio didn't work? I really would. That would be it. We'd be done. Direct comparison test. Okay, this really requires you to think. The direct comparison test says, if I can compare my series to another series, get it, comparison, I can make some assumptions about my series. It basically says, if I can take my series and if I can show that my series is bigger than a series that I already know diverges, then mine will diverge too. And if I can take my series and compare it to a series that converges and show that my series is even smaller than that, then mine will converge also. So let me say that more specifically. Let's say I know of a divergent series. Let's say I know of a divergent series and I'll call it d sub n. And I know I'm going to take my series and say my series is bigger. My series is a sub n. Well, if d sub n diverges, it's too big, then my series will diverge also. It's obviously going to be too big. So the first part of this says, if d sub n, hold on. If a sub n is bigger than d sub n, and the series d sub n diverges, then the series a sub n must also diverge. It makes so much sense in spoken English. It doesn't always seem as easy when we do a problem. But let's look at the converse of this. Is if I have a series, let's call it C sub n, that converges. So let's call this series C sub n, and it's small enough that it's going to converge. Well, if my series is even smaller than that, let's call it A sub n, then mine must converge also. Duh. Right? If I'm taller than this desk and you're taller than me, then you're also taller than the desk. It's kind of like transitive property in a way. If I'm, smaller than Kareem Abdul-Jabbar and you're smaller than me, then you're also smaller than Kareem Abdul-Jabbar. You also converge. How'd you like that little analogy? Came up with that on the fly. So if I were going to say this officially, if my series is smaller than another and C sub n converges, then my series must also converge. Boom. So it makes sense, and you really do have to just think it out and make sure you're thinking about the right thing. So let's look at this series. Does this converge or diverge? So again, nth term test would tell me I should keep going and keep testing this. This is not geometric, but here's the little spoiler. This actually, I can use the integral test for this, can't I? Can't I know that, the lights! Can't I know, don't I know, this is going to converge by the integral series test anyway? Whoopsies. Well, let me just show you how it would work with the direct comparison test anyway. So I would say, if I want to use the direct comparison test, I would need to say something like, we know that the series 1 over n squared converges. And I do know that. By the integral test, I do know that. Because my series has more in the denominator, it must be smaller than that series. Therefore, do we know those three dots mean therefore? That's what these three dots mean. Therefore, 1 over n squared plus 1 also converges. That's what the direct comparison test says. In this example, I would have used integral test if I had it from scratch. In the next example, we're going to have to use direct comparison test. So this wasn't a bad way just to see what I'm talking about. So if I can think about, I know a series that's really close to this that I know converges, and this is even smaller than that, sweet, that converges too. All right, how about this one? This is the first time we're seeing factorials. So this test is one you're just going to hate because you really have to pull stuff like out of midair sometimes. So when it comes up, I don't know, we'll work through it together. But this is the general idea. Okay, this series, I don't know, it looks crazy. But guess what? This series, I do have something I can compare it to. That's what I'm going to be doing with this direct comparison test. I'm going to be comparing it to another series. So I'm going to be thinking about, is this a series that I know? Well, this actually is really similar to the series for e to the x. Grab that little pink piece of paper. I think I have mine over here. This is where you're going to be like, Miss Dan, you just crazy. You crazy, you think we remember this. E to the x. Okay, guess what? The series for e to the x, which we know converges, is a bunch of terms, but the general term is x to the n over n factorial. That's the series for e to the x. Well, look at the series that I have. It's really, 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 really similar. The only difference is that this has a power of n. So this series is definitely smaller. So because I know the series for e to the x converges, and I know that my series, x to the n over n factorial to the n, is smaller than x to the n over n factorial. Therefore, by direct comparison test, my series converges. I think the direct comparison test is easy enough to understand. The question is, could you pull that out of your rear in a test situation? I'm going to say no. Just kidding. We'll see. We'll get better at it. But that's the idea. Take the series that we're given, realize, oh, that's really similar to this. And the one I'm given is even smaller than it. So since the one I know converges, the one I'm dealing with also converges. Well, ladies and gentlemen, there's your notes on the first 4 series convergence tests. I would imagine you've had a delightful time. Tune in next time when we discuss the ratio test. Actually, next time we'll probably be discussing example problems, or perhaps we'll be doing that live. You never know. I'll leave you with this thought. When you wash your hands, are you really washing your hands, or are they washing each other?